last time we spoke earlier about the Fibonacci sequence, and we looked at the ratio of successive terms of the Fibonacci sequence and found that it converged to this so called golden ratio, which is 1 plus square root 5 by 2. And then we realized that that method which was used to find a formula for the nth term of the Fibonacci sequence can also be used for more general recurrent sequences given by recurrence relations. And we looked at a second example of a sequence which is almost modeled on the Fibonacci recurrence, where the n plus 1th term was given by 2 times the nth term plus the n minus 1th term and so on. And we found there that instead of the golden ratio, these successive terms converge to 1 plus square root 2. And that could actually be used to find some nice rational approximations to square root 2. You could just take successive terms of that sequence and subtract 1 from it, and what you would get would be some rational numbers which approximate square root 2. So let us look at square root 2 a little bit more closely this time. Now what we are going to do is to try and construct yet another rational approximation, a sequence of rational numbers which approximate square root 2 or which converge to square root 2 using yet another idea. And this time we will sort of do something rather surprising and strange. Recall that we had the Euclidean algorithm. Okay, so what was the Euclidean algorithm? It was actually used to find the GCD of two numbers. So if you recall how the Euclidean algorithm worked, if you had to find the GCD of say 189 and 35, which was the example we had looked at back when we talked about the Euclidean algorithm, we find, so this is for the GCD. So we keep dividing one by the other and we take the remainder, then you make the remainder as the new divisor and the old divisor as the new dividend and so on, right. So it is actually the following process. So let us just depict it diagrammatically. So what are we doing when we actually implement the Euclidean algorithm? So what are we doing when we are implementing the Euclidean algorithm? Let us depict it on the number line. So let us draw the number line here and let us mark some points off. So we have 0 and we will write our divisor and dividend also on the number line. So I have got 35, which is the smaller number, right. And what we do is we divide 189 by 35. In this case we know that it divides 5 times. So 70, 105, 140, 175. So we have taken 5 lengths of 35. So 3, 4, 5, and we have our number 189 here. Okay, so beyond this, of course, you can't, it won't divide one more time. So what you are left with is actually a remainder. Okay, and this bit here is the remainder. So this remainder in this case we know is 14. So it is as if you are trying to measure, okay, this distance of 189, say 189 meters, but all you have is a scale whose length is 35 meters. Okay, so what you do is you try to measure this length. So you keep placing the scale of length 35 on that initial rope of length 189, and when you get to a point beyond which you can't divide, at that point you are left with a little bit of rope, right, and that is the remainder, that is the 14. So you sort of use that as your new ruler. So you now have, imagine you have a new scale of size 14 meters, and using that you try to somehow measure the original length of size 35. So now the two numbers which come up in the Euclidean algorithm beyond this are 35 and 14, and you divide 35 by 14, and well, it divides exactly twice. So here's 14, 14 twos are 28, and then you are left again with a remainder, in this case a remainder of 7. That becomes your new ruler, and now 7 divides 14 exactly, right. So I have got 0, 14, and my ruler has size 7. So exactly 2 lengths of 7 will give me size 14. So, this is sort of what we are doing diagrammatically when we are doing the Euclidean algorithm. Okay, so now what does root 2 have to do with all of this? So, here's the point, why not just try and do this with 1 and root 2. Okay, so what do I mean by this? So, let us imagine drawing a number line as before. Okay, I will draw it a little larger now in scale. So, I will mark off the number root 2, which as you know is approximately 1.414 etc. Now, I am going to measure a rope of length root 2 meters, but the scale I have is of size 1 meter. Okay, I have a meter scale. So, here is 1. So, what I have is this ruler here of size 1 meter, and using this I am going to try and measure this rope of length root 2. Well, what happens? Well, when I sort of place this ruler on top of this rope, I can only place it once and I am left with some remainder, right. So, this little bit of rope is left over, and how much is this? Well, this is exactly, so let us call this remainder as the first remainder R1, which is square root 2 minus 1. Okay, now I attempt to just do the same sort of procedure as in the Euclidean algorithm. I will use my new remainder R1 as my new divisor, and I will try to divide the original number, which is 1, the original divisor 1 in this case, by root 2 minus 1. So, what is the idea again? So, let us draw yet another number line. So, in step 2 of the Euclidean algorithm now applied to these numbers 1 and root 2, 1 is my given length, and I am trying to write it as multiples of this length root 2 minus 1. Okay, so, this is my number R1, which number is root 2 minus 1. So, it is roughly 0.4, and so 2 of these lengths. So, maybe I should draw it a bit better to scale. So, maybe that is 0.4, roughly 0.8. So, this is R1, 0.414 root 2 minus 1, this is 2 R1. So, it will divide twice, and again I am left with some remainder, right. So, what is that remainder? This is the second remainder R2. Let us see what the second remainder, it is just 1 minus twice R1. Okay, and R1 is just square root 2 minus 1. So, I can just substitute that into that. So, it is 1 minus 2 times square root 2 minus 1, and if you care to simplify, this is just 3 minus 2 root 2. Okay, so, I get a second remainder. Now, I keep going like this. So, I just again draw my number line. Let me draw it again a little larger to not the same scale as the previous one. So, now my dividend is R1, which I am going to try and divide by R2, right. So, how will we do that? So, what is R2? So, remember R2 is smaller than R1, that is guaranteed because of the way we do the Euclidean algorithm. We try to divide it an integral number of times, and then we are left with some remainder. When we do it with integers, the remainder is some integer, but here we are doing it with some real numbers. So, well, we are sure that the quotient is still in an integer here, but the remainder, the leftover portion, is some real number again, which is smaller than the real number that you are dividing by. It's smaller than the divisor. Okay, the divisor is again a real number. So, we are just trying to generalize the Euclidean algorithm, but now we are playing with real numbers instead of with integers. Okay, so I try doing the same thing, R2, which is 1 minus 2 R1. So, I try to see how many times R2 will divide. Okay, and so R2 turns out, we will just see this in a minute, R2 will again divide twice. Okay, so R1 is roughly 0.414, R2 is slightly smaller than half of that. So, it divides twice, and then again we are left with some remainder, which is R3. Okay. So, this remainder R3 now is, if you wish, it is R1 minus 2 times R2. Okay, again you substitute everything in, it is root 2 minus 1 minus 2 times 3 minus 2 root 2, and well, what is that? That is going to be minus 1 minus 6, so that is minus 7, and I have 4 plus 1 5. So, it is 5 root 2 minus 7, okay, and so on. So this is what I can keep doing. Now I should sort of say why it divided exactly twice and not more. So well, maybe we will just do it once we find the formula for the r's. So okay, so we keep going. So this is the Euclidean algorithm applied to 1 and square root 2 just means you keep doing this process, okay, at every time, every stage getting some real numbers. So let's write out the various steps of the process. The very first step, I divide root 2 by 1. So I get some quotient. The quotient initially is just 1 plus some remainder. The remainder is root 2 minus 1. Now I divide 1 becomes my new dividend. I divide it by R1. It happens to divide twice and gives me a remainder R2. Okay, and R2 we computed was 3 minus 2. Now let's do it once more. So this is R1 becomes my new remainder, and I said it divides exactly twice and leaves you with a remainder R3. And R3 we computed is 5 root 2 minus 7 and so on. Okay. So firstly, what is it that we are doing? So if you sort of observe what's going to happen at every step is that it will divide it exactly twice and leave you with some remainder. Okay. Okay, so what's going to happen at every step, as we'll soon see, is that each step of the Euclidean algorithm, when you divide the remainder Rn by the previous, rather by the next remainder Rn plus 1, what you'll always get is a quotient of 2 and some new remainder. Okay, so let's first convince ourselves that the quotient at every step is 2. Okay, so here's the first question. Why is the quotient equal to 2 at each step? So let's look at the very first step, or maybe the second step, depends on how you think of it. So I have to divide 1 by square root 2 minus 1. So this is 1 by R1. So I claim that when I do this, my quotient, my whole number that I get is 2, and then I get some new remainder which is smaller than R1. Okay. So let's divide 1 by root 2 minus 1 and see what this real number is. Well, I can just multiply and divide by root 2 plus 1, and when I do that, this is what I get, root 2 plus 1 by root 2 squared minus 1 squared. So that's just root 2 plus 1. Okay, now root 2 plus 1, recall, is what's the whole number here? It's 2, and what's the remainder? Well, the remainder is just root 2 minus 1. Okay, so observe that 1 by R1 is just nothing but 2 plus R1. Okay, so this is actually just 2 plus R1. Okay, and therefore, so I will rewrite this step as, so I am going to try and get something that looks like the Euclidean algorithm. So I have divided 1 by R1. So now let's go back here. So look, I had 1, I divided it by R1, and I am supposed to get some remainder R2. Now what I have observed with these actual numbers is that 1 is nothing but 2 times R1 plus a number R1 squared, but observe R1 squared is actually smaller than R1. Okay, why is that? Because R1 after all is a number smaller than 1, right? R1 is roughly 0.4. So if I square R1, I just get back something smaller than R1. So I have noticed that this equation holds, 1 equals 2 R1 plus R1 squared, and so this means that when I do the Euclidean algorithm, so Euclidean, the division algorithm if you wish, with 1 and R1 must give exactly this equation, must give this equation, right? Must give 2 as the quotient. And in fact, what is the remainder? R1 squared as remainder. So we actually got a little bit more. We tried to see what the quotient was, why the quotient was 2, but we also deduced that the remainder is in fact R1 squared. Okay, so therefore, at this step the quotient is 2, and the remainder, which we called R2, is actually the square of R1. Okay, now let's keep going like this. So what was the next step of the Euclidean algorithm? We took R1 as the new dividend and tried to divide it by R2. So let's do that. So I take R1 and I divide it by R2, okay, and then I want to see what is my quotient and what is my remainder, right, what is the whole number and what is left over. Now R1 by R2, remember, is just R1 by R1 squared. So that is actually 1 by R1. So in fact this is just the same equation as before, right. I already wrote out what 1 by R1 was and expanded it and figured out that the quotient is 2 and the whole number is 2 and what is left over is R1. So I already know this is 2 plus R1. So what does that mean? So I conclude R1 by R2 is 2 plus R1. In other words, when I do the division algorithm, R1 will give me 2 R2 plus R1 R2. In other words, I get 2 R2 plus R1 cubed. Now observe again that this is exactly what you expect to get in the division algorithm. I mean, this is the remainder you expect to get. R1 cubed in this case is definitely smaller than whatever you divided by. I claim R1 cubed is smaller than R2, but observe the term that we have here, R1 cubed, is actually smaller than R2. Why? Because what is R2? R2 is actually R1 squared, right. So R1 cubed is surely smaller than R1 squared because R1 is a number smaller than 1. So this means that therefore the division algorithm or the Euclidean algorithm in this step, Euclidean algorithm with R1 and R2 as the dividend and the divisor must give, what is the quotient? The quotient is again 2, that is this 2 here, and what is the property that the remainder is supposed to have? It is a number that is smaller than the divisor, right, so that I can't divide once more. So in this case, since I know that R1 cubed is smaller than R1 square, I cannot divide it more than twice. So quotient has to be 2 and the remainder is in fact R1 cubed, okay, and so on. So if you sort of now continue this process, what you will find is that when I do this division algorithm at every step, so I only have the first 3 steps really here, but if I keep doing this, then at every step I just keep generating my remainders which are smaller and smaller. I mean, they are all powers of the original R1, okay. So here is the problem for you guys to try out as an activity. Here is a problem: prove that what we are calling the Euclidean algorithm applied to these real numbers this 1 root 2 never terminates, it never stops, okay. Unlike if you started with 2 integers, then the Euclidean algorithm is guaranteed to stop at some point and give you the GCD sort of as the very last remainder, but with 1 and root 2 it never stops, it just keeps going on. And in fact, not just that, if you do the nth step, so we kept doing all the various steps starting with the first one, root 2 is 1 times 1 plus R1, which is root 2 minus 1. So this is the first step. The second step, if you remember, is 1 is divided by R1, R2, R1 becomes 2R2 plus R3 and so on, and in general this is how it will always look. The nth equation looks like this: 2Rn plus 1 plus Rn plus 2, okay. This is for all n greater than or equal to 1 if you wish. So this is in fact, it's very much like the Fibonacci, the recurrence sequence that we constructed after the Fibonacci example, except in this case, the R's are, see there we had the nth term was twice the previous term plus the term after that, so the term before that. Here it's like, it's an infinite sequence which starts from 1, 2, 3 and so on, in which every term is 2 times the next term plus the term after that, okay, and it's a sequence of real numbers in this case rather than a sequence of integers, okay. Also show that R1 is root 2 minus 1 and the nth remainder just turns out to be root 2 minus 1 whole power n. Okay, more generally Rn is just R1 power n.